This is our second video in the series about how to choose a loss function for our logistic regression classification model. In the last video, we hopefully convinced you of the pitfalls of using squared loss. And so now, to build up the theory behind the loss we are going to use, which is called cross entropy, we are going to introduce the idea of maximum likelihood estimation. So that's what we'll be doing in this video. So an easy way to think about this as a starting point is what I'm going to call the no input binary classifier. Suppose you've observed some outcomes, and I guess we can think of it as a coin here, but it's even better if you're thinking it's just some outcomes that are binary. So you don't get stuck in your own preconceived ideas about coins. But basically we have some outcomes that are zeros and ones. And I just want to know for the next flip, do you predict heads or tails? Right? What would you classify the next flip as being? So one way we can reasonably start to model this is to assume all flips are independent, identically distributed. And I then have a parameter theta that I could let that parameter represent the probability that my flip is equal to 1. And then based on that probability, I can make a prediction. Whether or not I think the next flip will be 0 or 1. So I really want to estimate that parameter theta. So out of the options below, using just the data you have, which is the best estimate for theta and why? And then once you have that estimate, for the next flip, would you predict a 1 or a 0? All right, there's multiple ways to think about this, but one reasonable way to think about this is to say, well, there were 4 out of the 10 flips that ended up being 1. And so we could use the frequency of heads in our data as our best estimate for theta. We're going to see in a minute that that's also reasonable because it maximizes what's called the likelihood of our data. So let's assume that we use this 0.4. Now I have to make a prediction. So for the next flip, would you predict 1 or 0? Well, since 0.4, I'd say I have a 40% chance of heads, I'm more likely to predict tails, right? Which is the most frequent outcome in the sample. That is one way to set up this classifier. All right, let's dive into some of the math that will provide us some justification for using this type of reasoning. And I want to point out this is not the only valid way of coming up with a classification for this type of data. But this is one way, and it actually has some pretty cool math behind it to give it some nice justification. So this is actually a problem you've worked on in an earlier assignment. At the beginning of the semester, we had you look at output just like this and come up with the likelihood. So that is the probability of observing exactly 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, given that the probability of heads was p. We don't know what p is. So the likelihood function is this p to the 4th times 1 minus p to the 6th, because I had 4 heads, and then I have 6 tails, and we're assuming they're IID. We can see visually this is going to be maximized when p is equal to 0.4. And you proved that on a beginning assignment. You can do that using calculus and also visually via the graph. So just pointing out an example of what we could say is a bad estimate for our parameter would be p is 0.1 because the likelihood is pretty small of observing the training data that we saw. An example of a good estimate, again, we said was 0.4 because that gave us the highest likelihood of observing the training data. So let's generalize this. And so for our training data, we had 0.4 is the most intuitive. And because it's the frequency of the heads and it maximizes the likelihood. So here's the math form of writing that. There's the likelihood function. Argmax says find the theta that maximizes this function, and that's what we're going to call theta hat. Then we would use that, as our probability here, and then based on that we can make a prediction. We would classify into either group 1 or 0. So how can we generalize this notion of likelihood to any random binary sample? So think of your data as just being ones and zeros. And if you're thinking, oh, this looks kind of like the data we've been working with in our logistic regression model, that's not an accident. So your Y, your outputs here are just ones and zeros. And I would like to find the theta that maximizes the likelihood. All right, so one way we can think about this, let's first assume that each of these data points are Bernoulli, so they can either be 1 or 0, with probability P of being 1. And for this first scenario, we're going to assume they're independent, identically distributed. So for any one Y value here, like we'll think of Y sub 1, the probability that Y sub 1 is equal to 1 is going to be P, and the probability that it's equal to 0 is going to be 1 minus P. You can see that in here because I'm going to plug in if Y is equal to 1, only this term stays. If Y is equal to 0, only this term stays. So this is a nice compact form for this was a PMF, if you remember, for our Bernoulli distribution, but this is the closed form version of it, which is just going to be useful for us in this context so that I don't have to write it as this piecewise function. Okay, now I'm just going to add in one more piece. So now if the binary data are IID with the same probability, then the likelihood of all the data in my sample is going to be, well, I'm going to take this probability and multiply it for each data point that I have. And that's really what's happening here. It's showing you for each data point, and this is just shorthand notation that says multiply everything inside here as you increment over I. So I'm just going to have this long product, and this, if I were to do this for this data here, let's just look. So if Y sub I is 0, I'm going to come over here, I'll have P to the 0, so that's just 1, and then I'll have 1 minus P to the 1. So I will get a 1 minus P just for that first term. And then you're going to see every time I have a 0, I'll get a 1 minus P. Every time I have a 1, I'll get a P. So this is just a short mathematical notation for us to write this concept down and generalize it for any number of data points. And we can actually generalize it even further. We're not stuck at assuming that they all have the same probability P. Let's assume they each have different probabilities, P sub I. So now they're not identically distributed. Now they're each their own Bernoulli distribution with some probability. I can still write the likelihood in a nice compact form, right? So this is the probability of observing the data I did. Okay, so ideally, for maximum likelihood estimation, ideally what I'd like to do is now choose parameter values, so choose probabilities P1, P2, Pn, that maximize this likelihood. So given the data I see, what are the probabilities that make that data the most likely? That's a reasonable formulation for trying to decide what your parameters should be. And you'll see this is common practice throughout machine learning. So I want to maximize this product. If you recall on that first assignment, you had to maximize this product in a simpler form as well. And I gave you the hint to use the property of logs. So the math trick here is I can take the log and then maximize the log of this product, and I will end up getting the same p-values. So this is, again, just saying that the maximum of this quantity will occur at the same p-values as the maximum of the log of this quantity, and the log is just much easier to work with because it basically allows me to break up products into sums, and sums are just much easier to handle when you're doing maximization. So these are just a few log tricks here that gets us to this form. This is the equivalent as this, and I'm just going to try to maximize this now. And equivalently, I'm just going to put it in a form that you'll also see. Maximizing this function is the equivalent of minimizing the opposite of it. So I'm just putting a negative out front, and I'm going to divide by n here just because this is going to look like, a mean of something. And sometimes we want to take means in our loss functions. This is giving you a little bit of a taste coming ahead. Adding this little -1 over n out front and saying minimize is not going to change the p-value, p1, p2, pn that I would get. So it's just a mathematical convenience to get this in a form that I can think of it as an average loss. Okay, so that's what we're going to do. We're going to try to minimize this function, and that's equivalent to maximizing the likelihood. So that's the idea. And you did it. Like I said, this looks fancy, but you did this exact process for one specific data set in your original homework. So now we're just generalizing it. Okay, so let's see how we can use this to justify the loss function we'd like to use for logistic regression.